You've seen two very similar results regarding the error analysis for the Euler method, and I figured that a small drawing might help you to understand what these two error estimates are about. So suppose I've got a Cauchy problem, u prime of t equal f of t u of t, with initial condition u at 0 is equal u naught. And here in the screen you see a drawing of the graph for some function which solves some Cauchy problem. Now let us assume that we apply the Euler method with some step size h. We start at time t naught equals 0. Next time step is h, then 2h, 3h, 4h, and so on. And each of these time steps is called t1, t2, t3, t4, and so on. At time t naught, the Euler method and the true solution agree that it has the same starting value u naught. And then the Euler method reduces values u1, u2, u3, u4, and so on, which sort of approximate the values of the true solution. So u1 is an approximation of u at time t1, u2 is an approximation of u at time t2, u3 is an approximation of u at time t3, and sometimes the approximations are quite good, and sometimes there's a significant error in the approximation. What the first error estimate is about is bounding the error in the approximation at these discrete time steps. I've got these discrete time steps where I try to approximate the function u, and the error estimate tells me an upper bound, how far that approximation can be removed from the true solution. Many textbooks on numerical ordinary differential equations actually stop at that point and are only concerned with the approximation at these discrete time steps. Our first error estimate produces precisely that, an approximation estimate for the error at the discrete time steps. The approximation errors that I've drawn here can also be used to define an approximation of the entire function u. The Euler method has produced approximations of u at the time steps t0, t1, t2, t3, and so on. And suppose I want to know an approximation now for some time in between. Now, one thing I can do is to connect these points that the Euler method has produced by drawing a few lines. The blue curve here is composed of line segments, and it defines a piecewise linear approximation of the function u. Now let's suppose I want to have an approximation of u at some time that lies between two time steps. For example, we can take the linear interpolation to get a value at time 5.4h in between t5 and t6, and use that value as an approximation of u at time 5.4h. Now, taking a look at this dot on the blue line, that is supposed to be an approximation of u at time t equal 5.4h. We can again ask, okay, what is the approximation error? And that question is precisely what is answered by the second error estimate that we have derived. The first error estimate was concerned about the approximation error at the discrete time steps. And the second approximation estimate was concerned about the approximation errors if we consider times in between the discrete time steps. Now, if we take this blue line here as an approximation for this entire function u, then the very nice consequence was that we can use the same formula for the error at the discrete time steps and the times in between the discrete time steps. Using the formalism of the second approximation estimate, for example, we can write 5.4 times h as t5 plus tau, where tau equals 0.4h. In order to put a bit more life into that error estimate, Let us discuss two more examples. Let alpha be a positive constant and consider the Cauchy problem u prime of t equal alpha times u of t with initial condition u of 0 equal 1. By this point, you should all know the solution to that differential equation, to that Cauchy problem. Namely, the solution is u of t equal exponential of alpha times t. Now let us suppose that we apply the Euler method to this very simple Cauchy problem. Let's say we are only concerned with times within the interval from 0 to 1, and we have step size h. What is the approximation error that I encounter with the Euler method for this model problem? Of course, I already know the solution to this model problem. However, such simple model problems where we already know the solution are very good test cases to try out a numerical method and get an idea of how this method actually behaves in practice. In order to instantiate the error bound for the Euler method, I need to know at least two constants, namely L and M. L is very simple to find. As you can tell, the right-hand side of that differential equation, FTU, is just given by alpha times u. So the distance of FTU and FTV for any times t and any scalars u and v can be bounded from above by alpha, the absolute value of alpha, times the distance of u and v. Since alpha is positive, we can simply put L equal alpha. It is also quite easy to find a value for M, since we already know the solution to this differential equation. U prime prime of t for any time t is given by alpha squared times the exponential of alpha t. And so we see that M can be chosen as alpha squared times exponential of alpha, using that t is at most 1. Now equipped with these two values, we can bound the approximation error for any time t. T is taken from the time interval from 0 to 1. So we take this formula, m over 2l times h times the exponential of L times t minus 1, and plug in the values for m and L. With very simple algebraic manipulations, I get that this upper bound equals h times alpha over 2 times exponential of alpha t plus alpha minus exponential of alpha. That upper bound is not necessarily tight. It's only an upper estimate for the approximation error of the Euler method. But the least that I know is that it is reliable. Before we get to the actual number, let's take a look at a few graphics here. What you see here are different approximations of the true solution of the differential equation u prime of t equal 2 times u of t, with initial condition u at 0 equal 1. At the top here you see the true solution, or at least an approximation of the true solution, the exponential of 2 times t. And you see approximations obtained by the Euler method with different step sizes, such as h equal 1/2, h equal 1 over 10, h equal 1 over 10, 20, and h equal 1 over 100. Well, you can tell that this approximation gets better and better as I decrease the step size. In particular, as at time t equal 1, we can tell that at every decrease of the step size, the approximation gets better and better and approaches the actual value of the solution at time t equal 1. Now, can we use the error bound to get an upper estimate for the approximation error of each of those approximate solutions here, the distance to this true solution here? And if yes, how good will this error bound be in comparison to the true error? So let's suppose I take t equal 1. So I use the Euler method to find an approximation of the solution at time t equal 1 with alpha equal 2. With that choice of alpha, I get that u of 1 is roughly 7.38905. And in this table here, you see the results that I get for the Euler method with different step sizes h. So in the first column, you have step sizes h equals 0.5, 0.1, 0.05, 0.01, and you decrease the step size further and further. The second column shows the approximations of u1, which the Euler method produces. If the step size is 0.5, then the approximate value of u1 is roughly 4.0, and as you can tell, as the step size decreases, I very quickly get close to the actual value. The third column depicts the error in the approximation. As the values in the second column get closer and closer to 7.38, the error correspondingly decreases and gets smaller and smaller. The fourth column shows the error bound with that particular step size h. As you can tell, as h gets smaller and smaller, so does the error bound get smaller and smaller. Finally, the fifth column shows us the ratio between the error bound and the true error. For example, with step size 0.5, the error bound is 23.6 roughly, whereas the true error is 3.38 roughly. The ratio of the error bound versus the true error is roughly 6.9, which is quite some overestimation. But as the step size decreases, we see that the error bound typically overestimates the true error by a factor of roughly 3.9. By the standards of numerical analysis, this is actually pretty good. So it's only an overestimation by some constant factor. Let's take a look at another example. Suppose I've got the Cauchy problem u prime of t equal t times u of t over 1 plus t square, with initial condition u0 equal 1. In that case, the right-hand side of the differential equation is f of tu equal t times u over 1 plus t square. Now let's suppose I'm interested in the values of that solution. over the time interval from t equals 0 up to t equal 1. And I apply the Euler method with step size h to get approximate values, approximations to the true solution. If I now want to apply the error bound to get a rough idea what approximation quality is guaranteed, I again need to find values for L and M. Finding an estimate for L is again fairly simple. If I take some scalars u and v and some time t, then estimate the distance of ftu and ftv, then I see I'm actually just measuring the absolute value of t times u over 1 plus t square minus t times v over 1 plus t square. I can factor out t over 1 plus t square and only have the distance of u and v. And a very coarse estimate of this factor gives us that this is bounded from above by just the distance of u and v. So I can pick L equal 1. In fact, a more careful analysis of this factor t over 1 plus t square would lead us to the realization that we can pick L equal 1/2. But this is not essential here. Next, we're going to estimate M, which is a bit more complicated. In fact, our estimate for M is fairly rough. Nevertheless, it's a good exercise in numerical analysis, and it is fairly indicative of what you do as a researcher on numerical analysis all day. Now, we recall that M is supposed to be an upper estimate for the second derivatives of u. So probably it's a good idea just to compute the second derivative of u. That can be done just using the differential equation. We have u prime of t equal f of t u of t, which is u of t times t over 1 plus t square, And if we take the time derivative on both sides of the differential equation, then we get a formula for the second derivative of u. Concretely, we get that u prime prime of t is equal u prime of t times t over 1 plus t square plus u of t over 1 plus t square minus u of t times 2 times t square over 1 plus t square to the square. Next, we do another algebraic manipulation in order to get rid of this first derivative of u in the first term. So we use that u prime of t is equal u of t times t over 1 plus t square and simply plugs this in. That's how I get to the second line. Everything else stays the same. Now I do some very simple algebraic manipulations, and I get that the second derivative of u prime prime at t equals u of t over 1 plus t square to the square. So if I take the absolute value of u prime prime at time t, then a very simple upper estimate tells me that this is bounded from above by the absolute value of u of t. Next, I'm going to use an upper bound for u of t. In fact, we have got that f of tu in absolute value is bounded from above by the absolute value of u. And you can use an inequality from the homework to estimate that this u of t is bounded from above in absolute value by simply the exponential of t. Using that inequality from the homework, I get that u prime prime of t in absolute value is bounded from above simply by the exponential of t. Now, this is quite a rough upper bound. With some more careful analysis, of course, we could obtain a much tighter bound for the second derivative of u, but I've decided to keep it simple here in this presentation so that the successive formulas are a bit easier to handle. Okay, so we've got values for m and l, and we can plug them into our arrow bound. So the arrow bound for the Euler method at time t is m over 2l times h times exponential of l times t minus 1. Okay, t is at most 1, and plugging in the values of m and l and using that t is at most 1, I can simplify this to h over 2 times exponential of 1 plus t minus e, the Eulerian number. Okay, let us check again how this error bound measures up in comparison to the true error. So suppose I use the Euler method to get an approximation of u at time t equal 1, which is roughly 1.4142. And the results of various approximations are summarized in this table again. In the first column, I got the step sizes h. This time I've picked 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, and finally 1 over 64. So I halve the step size consecutively. And in the second column, you again find the approximation of u at time t equal 1 produced by the Euler method. We start with 1.2, then we get to 1.3, and you see that we're getting closer and closer to the true value. In the third column, you find again the actual approximation error. So we begin with roughly 0.214 for step size 1 over 2. And as I keep halving the step size, you also see that the approximation error gets halved. Now in the fourth column, by comparison, you find the error bounds that we have used here. So I simply take h over 2 times exponential of 1 plus t minus e, where t is equal 1, compute these values, and have put them into the fourth column here. So the first error bound is 1.167 roughly. And as the step size gets halved and halved, so do the upper error bounds reduced by this formula. Now finally, in the fifth column, you find again the ratio of our error bound and the actual error. So for example, for h equal 1/2, I have that the error bound is 1.67 roughly, and the true error is 0.21. So this error bound overestimates the actual error by a factor of roughly 5.45. That's a bit of an overestimation, but as the step sizes decrease, we see that this overestimation does not get much worse. So we can tell that as the step size decreases, the overestimation will be roughly by a factor of 5.154, something like that. So what we can tell again here from this table is that the error bound will be an overestimation, but at least it will be reliable. Now, after all these numbers, let's try to cool down a bit and have a look at these graphs here. What you see here are numerical approximations by the Euler method to the differential equation u prime of t equal u of t times t over 1 plus t squared, with the initial condition u0 equal 1. For example, here at the very top, you've got an approximation obtained by the Euler method with 100,000 time steps. It is still a mere approximation, of course, but for our purposes, we can take it as a reference solution. And here you see approximations with step size 1/2, 1/4, 1/8, and 1/16. As you can tell, as I halve the step size, so does the approximation error gets halved and halved. The error bound that we have derived for the Euler method overestimates these approximation errors, the distance between these curves here and this purple curve, typically by a factor of 5.1 and something, as we have seen. By the standards of numerical analysis, that is a very positive result. The error bound is reliable, and as I decrease the step size, the ratio between the error bound and the true error does not get worse and worse. It roughly stays the same. So to summarize, in this video we have seen two examples on how to use the error bound for the Euler method. We've seen a few typical calculations on how to find the parameters L and M for the error bound. And in the two examples that we have taken a look at, we have seen that our upper estimate for the error holds up pretty well in comparison to the true error. The ratio between the upper estimate and the actual error remains roughly the same in the two examples that we have seen. Now, the Euler method in some sense is a standard numerical method for ordinary differential equations. And one important consequence of our error estimate of our upper bound for the error is that as I decrease the step size h, the approximation error is guaranteed to decrease as well. However, pretty soon we are going to see examples of the ordinary differential equations where the Euler method, even though it is guaranteed to converge to the true solution as the step size decreases, requires significant computational effort in order to obtain a useful approximation. And that is going to lead to the development of a few alternatives for the Euler method. And specifically, we will have a look at what is known as the implicit Euler method in the next video.